Welcome to Advanced Insights, where we provide just what the show name suggests, advanced insights into some of the most exciting trends and topics in technology. On this episode, I'm joined by Ramin Hasani, co-founder and CEO of Liquid AI, and a machine learning scientist at the Computer Science and Artificial Intelligence Lab, or CSAIL, at MIT. I'm looking forward to what I think will be a very exciting discussion with Ramin. Ramin, I have been so looking forward to having you on our podcast because I think about what you and your startup are doing, and you're creating a sort of a new class of where AI can be deployed and how it can be deployed. And I particularly love it because you're rethinking how to optimize, like how AMD as a chip developer can work with you as a practitioner of the state-of-the-art AI to create this whole new class of AI computation. Great to have in this show, and I'd love to hear just your thoughts about Liquid AI, your startup, and how things are going.
Thanks for having me. Likewise, very much looking forward to this conversation. Yes, so Liquid AI, we are a foundation model company. We are building efficient foundation models. As you mentioned, we are rethinking how we design foundation models. Like, it's not just about quality. We are thinking about where intelligence goes, how AI is getting served, where AI is getting served, what latency you are getting out of the AI kind of feature that you're hosting. How much battery are you consuming? There's a whole world of AI and processors that exist outside of data centers. So we're talking about the device world, right? And this is where Liquid AI wants to focus on and really double down on that kind of market, which is kind of untapped. Not a lot of attention goes into the device world, but because there's a lot of technological challenges and breakthroughs had to happen for us to be able to truly enable the same level of AIs, generative AI kind of powers that you see on the cloud, to actually enable those things also on the device world. That was where we came in. Essentially, 3 years ago, spun out of MIT, Computer Science and Artificial Intelligence Lab, CSAIL. We started this company building on my PhD thesis and my co-founders' kind of decade-long kind of work that we have been working on a concept called liquid neural networks. The idea there was that let's take a step back. Let's look into what nature has taught us in terms of like computational units that is used in, let's say, brain of species, and in animals, like small animals. And then take a physical approach to bring a little bit more insights from how neurons perform computation in brains, take those kind of inspirations to machine learning, to the machine learning world. The whole thesis around this was the fact that we want to pack a lot more intelligence into smaller units of computation. So, for example, we wanted to power robots. The processors there are not. You don't have the luxury of kind of a very beefy GPU, but there you have like a processor that is smaller, and you need to be like really counting for every intelligence per watt that you are actually optimizing for, right? And so that was kind of the domain. And at the same time, this is a physical world, right? We are talking about bringing intelligence into physical world and onto smaller and low power kind of processors. So then we invented this technology, liquid neural networks, on the principles of how two neurons exchange information with each other. That was the start of the process. Modeling that allowed us to build very advanced AI systems for predictive robotics application, predictive finance, predictive healthcare. We showed at MIT during our research that how much you can actually do. Like, we showed that with a handful of neurons, you can drive a car completely, like, on a very, very little processor. If at the unit of computation, these models are extremely smaller than the alternative artificial neural networks that are solving the similar problem, maybe at scale, we can keep these scaling laws the same way and power generative AI, power new forms of computation.
Ramin, that is so exciting, and I'd like to dive a little deeper in exactly that. And just for our listeners, I'd like to highlight the huge contrast of the innovation you just described for LFM versus what they're all running on today when they go in the cloud. So if they go in the cloud, as you said, beefy GPUs, these are trillion parameter foundational models with this, vast knowledge base that's been trained. I think we could dive a little bit deeper, and folks would be very interested in that.
Whenever a technology actually starts, like you always have like the exploration phase. Then we start like learning from that kind of space, and we try to make that process a little bit more efficient. So that efficiency, like when we understand, when we mature in a certain kind of technological trend, you can see that how that affects efficiency. Like there is definitely kind of a trend towards making models more efficient, and making models like they're moving towards like smaller but more powerful, like without loss of quality. So intelligence per watt, like as kind of a measure, it is going up. So this is what is definitely happening. But what we are talking about at Liquid AI is like 2 orders of magnitude even smaller than what you just mentioned. We are talking about going from the trillion parameter regime to 100 million, or like basic between 1 billion to 10 billion kind of parameter regime. We are talking about really shrinking down the size of intelligence to the point, without sacrificing quality, to the point that you can deliver the same quality of those cloud models on the device, directly on the device. And that required like 2 different shifts of like thoughts and algorithms. Like we have done innovations across model architecture, like that change of model architecture, thinking about other primitives of computations. For example, perhaps like 99% of the generative AI today is powered by the architecture, transformer architecture, right? Or variations of this transformer architecture. But that's just matrix multiplication, and then ways that we can actually figure out how to perform matrix multiplication. There are so many other operators, like mathematical operators, that you can actually start exploring and seeing, like, can we build general purpose behavior with other types of, or maybe combination of other mathematical operators? That was the objective function at Liquid AI. We wanted to see, can we get, let's say, tiny models that optimize for memory. Let's say they can fit in, let's say, 1 GB of memory, which is like a very, very tiny space that if you think about it in terms of like today's models and generative AI models, reduce the memory size, increase the speed, reduce the latency of the model, while keeping the quality of the model at its highest kind of capacity on the job that they want to perform. But then thinking it from first principles, 2 innovation had to happen, as I was mentioning. So one of them was this model architecture that I alluded to. The other thing was that we thought about a systematic approach on changing the architecture. We thought about building a meta AI system that allows us to build a search space of possibilities, put the processor of use in the loop of that search space, and then go through basically seeing what should be the computational graph of a foundation model for a given processor. Imagine if you put an AMD CPU or an NPU or a GPU, like a consumer kind of GPU level. You're talking about like Ryzen AI PCs, for example, right? We are putting one of those units in the loop. Then what we try to do, we try to have a search algorithm to look over variations of computational graphs that run really fast. Like from the speed point of view, they're extremely optimized. From the latency point of view, they're optimized. And at the same time, from the memory footprint point of view, they are extremely optimized, while they are satisfying a certain benchmarks. For example, if you're talking about a knowledge worker that is powered on a laptop, you would be able to have a liquid foundation model designed for those CPU, GPU, NPU class, and then that architecture is going to be the most basically efficient variant of a foundation model that you can ever get, that is performing that job as good as the cloud models. So enabling this hardware in the loop approach that we took in designing foundation models and thinking fundamentally about different operators that can enable general purpose computer, this was the 2 innovations upon which we built liquid foundation models. And this is now enabling a completely new world, this new world of device foundation models. You can bring now all sort of technologies, all sort of exciting opportunities for AI agents that you've seen in the cloud directly onto the device. Use them for offline applications, for privacy critical applications, for decision critical application, for security air gapped kind of environments. These are kind of the range of opportunities that is fantastic, and I'm super excited about it.
I am too. In fact, I actually want to dive a little deeper in that. You spoke at the Consumer Electronics Show with along with Lisa Suet as she hosted the opening keynote. And what I love, and some of our listeners may have heard it, others weren't there. You talked about some exactly around use cases that could leverage that kind of low latency, so super quick response that could work offline, that can be proactive. Actually, if you could just share some of the use cases that are there now and what you see coming, even in the next few months.
You've seen the whole world of AI since the beginning of 2026 got dominated by AI agents and then sub-agents. Like you saw the OpenClaw like coming out of in January. But even before that, with AMD and with Lisa and your team, actually, like we've been like really working on this idea of not just bringing reactive AI agents onto, let's say, processors. Because if you bring an AI system that runs directly on a laptop, there is no reason for these systems not to be active all the time. So if an AI system can run in the background of the system, so in the background of a computer, you can think about all sort of productivity kind of tasks that you are reactively using AI. Like you're going to a chat bar, you're trying to complete kind of a job, and then the AI reacts and then coming back to you. But now AIs can become a lot more proactive. If AIs can consistently run on the device without interruption, and they are low power, so they are not damaging basically the battery, so the energy is controlled, then now you can enable something that I call proactive agents. They can perform a job that you actually given to the system, and they can really be an agent on your behalf. Like think about an assistant. Think about an army of assistants. So we are talking about agents and sub-agents being able to perform a lot of jobs for you, and that's the era that we are living in today. The most reliable version of these proactive agents, they live on the cloud. So you need to have the core brain of these AI agents to be extremely advanced and a good reasoning model. So that's why like OpenClaw kind of instances, you've seen like the most amount of success for OpenClaw kind of use cases has been use cases where the backend is one of the big AIs, like one of the ones like from Gemini, from OpenAI, or from Anthropic. Imagine if you could enable that on the device, directly on the device. That is the world that we are enabling. So we're talking about building brains that can sit on the laptop directly. So whenever you're even offline, whenever you want to give it some sensitive information about your health, about your taxes, about your financial situation, about your, let's say, secret project that you're working on the side that you don't want to like share it with the cloud, you can have all of those things like basically run directly on the device, and then enabling that agentic behavior, the same type of behavior that you're seeing from sub-agents and agents like taking a job and doing it for you, do that directly on the device. That's the world that we are enabling basically with liquid foundation models.
To take those type of agentic flows and to bring it into your device, to bring it into like an AI PC and run it so productively, I think is going to be a game changer. And we're just at the beginning. It can run offline and you can trust it, because if you run it offline, that's like an air gap between you and the rest of the world, and you can decide what gets connected to the cloud or not. How did you do that? Is there like special permissions? Is there auditing capability? What kind of things did you all do to help folks that want to run those kind of applications offline and on a device with your enablement?
That's a great question. So think about it like this. So the models are small enough that they can sit on an NPU that is powering the system. Let's say on a Ryzen laptop, for example. So you're going to run liquid foundation models. Like we've been working together to optimize these things to run on NPU. The reason why you have to run it on NPU for sustained kind of work, NPUs are kind of the low power, kind of like, this is like the place where you can actually compute with lowest possible kind of power. Therefore, it's like really good for the health of the battery. Therefore, it's like really, and it delivers like a lot of, like we're talking about like 50, 60 tops, right? That's kind of the range. Like this is a massive, like we're talking about having like and almost a supercomputer if you think about in decades on your hand. So what we are trying to do, we're trying to bring liquid foundation models directly running, sustaining a job on your NPUs. And we're not just talking about one liquid foundation models. We're talking about an army of liquid foundation models. Each of them are specialized for doing something on top of your computer. Now, as you mentioned, in order for this sustained activity to be done in a verifiable way, you need to have models to be able to actively check the actions that are taking. So you have some models, you task the models, you build the whole system to be able to not just take a command and then execute the command, but also iterate over like the commands that is actually performing. So you can increase the verification resources that you provide to the system in order to add the reliability of execution. And then why this system stays very safe, because this system never leaves to any other, never reveals a secret outside world. You can put completely your computer offline, and you can still perform all sort of heavy compute tasks that you want to perform on a computer, be it like processing, like let's say you want to write an essay, like like about a certain topic, and that essay has it has to touch some confidential documents that you have in multiple places across your workstation, so it has to pull information in many different kind of sensitive kind of data that it has to pull from different places. And for you to collect all of that data, you're not revealing any secrets to anyone. So because the whole computation actually happens directly on the device.
I love that. Even today, when I'm really researching a particular question that is very important to me, I don't run on one model. I run on multiple models and I compare it. I haven't yet created that as an agentic process. You built it in. That agentic workflow, you built it in as a part of the LFM architecture. I love that. What I'm thinking too, you talked about the energy efficiency you gain with this approach, as well as different math approaches, different transformers architecture that you're thinking of, and it brings to mind to me a fear that I'd like you to comment on. The fear in the world is, okay, AI is great, and oh my God, look at these agentic workflows and all the productivity gains we're getting. It drives so much energy consumption. We have gigawatt data centers, and we'll of course continue to need that for these massive problem sets that are run on these huge clusters of high performance CPUs and GPUs or specialized accelerators. What do you think and your team about these new approaches? Do you think it will help us even more broadly drive efficiency to AI applications in the future?
We are talking about designing for processors. Our approach allows us to have a hardware in the loop, processor in the loop, and design these foundation models. That approach allows us to bring in any type of processors in the loop and design for those foundation models, so design for those kind of processors. For example, if you think about even data center GPUs, our models run extremely fast on even GPUs that are hosted in the data centers because they're optimized for processors. We can have a different computational graph, different kind of inference stack, around that model so that it can run extremely fast. We are talking about completing an LLM job in 20 milliseconds. That fast, and this is kind of the cornerstone of anything that you want to do. Any kind of, solving really complex tasks requires, and in a short period of time, requires, you to hit this type of latencies. We're talking about audio is actually emerging as one of those places where, humans like to interact with systems, and then audio is important, and the latency in audio interaction is extremely important. So our models are fundamentally kind of multimodal. They can process audio, they can process vision, they can process text, and even alternative signals. Audio is extremely important. Then transaction data are also important. If you think about financial applications, like financial services application, there are high frequency decisions you want to make at certain kind of points. These are kind of places where low latency applications of this AI becomes important. So designing for efficiency, efficiency being the DNA of our company, it allows us to unlock latency that was not even possible before, even on the data center applications. And we really need that, Mark. As you know, like, we don't have enough energy in the world right now to power the demand that exists for generative AI. Everybody's working on efficiency one way or another, and I think our approach is helping us to fundamentally think about it from a technology, whatever that is possible. We are trying to juice out, like, from the algorithms side of things, to really have like the best version of a computational graph for deployment on any type of processor, be it hosted in a data center or outside of data center.
That is so important. Just step back. Just think from a society point of view. I mean, it's an incredibly exciting opportunity to bring just much more efficient AI computation. I have to ask, of course, given my role at AMD, we are very, very focused on open source software, an open ecosystem. How does that play with your goals? So we have a ROCm stack that's open, even our optimizers on an NPU, the Iron Optimizer and other tools that we have, they're Lemonade. I mean, they're all open source. Tell me about you and your team and how that plays.
Coming out of academia at MIT and even before that at Vienna, I was like, open source was extremely dear to me. So, and I believe that science has to be shared. So we have this DNA of really like open source being an extremely important aspect of our work. So last July, actually, we started open sourcing heavily, and with really fast cadences, like releasing liquid foundation models to the community. We are releasing liquid foundation models as open weight. And we saw unbelievable kind of demand from the market. From last January, after the CES event that we did with Lisa, we started hitting 1 million downloads of our models every week. And it is so interesting to see how the community is building, what type of solutions they're building around it. It's definitely helping us with distribution and awareness also about this device foundation model world. I really admire also like companies like yourself, like the category defining companies like yourself, in the hardware layer of all of this world. I think your commitment to open source is also extremely important, right? Like, we as a smaller player, we are chasing the distribution, I would say. Like, we are being honest, and this is what it is. And at the same time, we're providing access to the technology. But it's coming from a category leader like yourself. It's extremely valuable. I mean, we have seen the rate. I've seen the rate of improvement on ROCm and also the ecosystem itself. It's unbelievable. Like, now we can run training jobs on really like larger scale kind of lump sum clusters, which was not possible before. And that's really good to see, because I think open source is tremendously gonna help access to this level of kind of intelligence that we need from the bottom up, because you guys are sitting at the layer which defines all of these elements of generative AI, basically, which is extremely important.
Well, I love that we're so like-minded there, and I'm looking forward to even more collaboration. I always like to wrap these conversations, Ramin, with a look to the future. You are cutting edge, as you said. You came out of the CSAIL lab at MIT, and you and Daniela have just always challenged thinking. You're redefining with liquid AI, how we can go about creating efficient. Such incredibly more efficient AI computation. What is your thought going forward? I mean, are we, are going to see more AI native thinking about how to end-to-end optimize, how to become even more efficient going forward? What are some categories of breakthroughs that you feel would be ripe to pursue, and that you are driving in the coming months and years? I always say coming years, but in AI time, you have to say like days and months.
100%, yes. My vision is that, like, I want to power foundation models at the layer of all the devices around the world. We are talking about today about 2 billion processors every year can host a liquid foundation models on top of them, realistically. Off of the 35 billion processors that are getting built, like microcontrollers, across microcontrollers, CPUs, NPUs, GPUs. So there are 35 billion. 2 billion of them are being able to power liquid foundation models. And this is kind of the 2 billion is basically the one that we want to start. Like, this is across phones, laptops, tablets, like you name it, cars, and then other devices, right? So that is where we want to go. Efficiency is allowing us to be able to basically democratize access to intelligence, right? Think about places where they do not have the AI infrastructures for, let's say, building like massive data centers, like in there. These are the places where you can bring liquid foundation models on let's say, on a computer that they are doing their jobs, people that are performing their jobs, and you can provide that access to intelligence. Even if they don't have access to internet, they can get access to intelligence. This is kind of the distinction that we are making with this type of technology. So device world becomes extremely important. So that's one of the directions that we are going. The other thing is that from a technology point of view, from a company point of view, we are sitting at a foundation model layer, and we want to work with hardware providers like yourself to really closely bring in this fabric of foundation model layers to be so intertwined with the hardware, so that the next generation of hardware is already kind of the base of intelligence and base of agents. If you think about the stack, I always describe the stack of generative AI. There's the hardware and processor layer, you have the foundation model layer, then you have the agents, and then you have application, right? So now application is now getting blended into the agentic kind of world, because agents are like now directly taking the demands to the clients, and they can perform the jobs directly. So software applications are getting a little bit fuzzy, like, the definition of those things, if you think about it. So agent layer is like something that is, we can talk agentware, like from now on, like this would be like the thing that is going to be out there. But then the foundation model layer is something that is enabling the agents. But imagine if the foundation model layer from a software perspective gets so integrated into the design of the hardware itself, so that you can directly enable agents. Once you get a processor, you're already having access to the best type of intelligence integrated in your chip. So I would say, from a liquid AI standpoint, working with partners like yourself is extremely important to define what is the hardware software co-design that allows us to bring in foundation models and chips to be one layer to enable kind of the agentic layer on top of, be it in a data center or outside of data centers.
Ramin, it's music to my ears. Listeners of my podcast know I hit this concept of holistic design, the optimization from silicon all the way up to the application, and probably with almost every guest I talk to, because I think it's central. I couldn't have a better proof point than with what you are doing at Liquid AI and the societal benefits of democratizing AI and driving sustainability across AI computation. It's an incredibly exciting time, and so happy to have you on the show, and I can't wait for what innovations are coming next.
Mark, I can say with confidence that I think we have an exemplary kind of partnership together. So, and it is extremely important to stay close as we are actually building the next generation of foundation models, the software kind of ecosystem. Times couldn't be like better that for what we are doing. And I'm very, very grateful for all the support that we are receiving from a great partner like AMD.
Fantastic. Thanks so much, Ramin.
Thank you.
I truly enjoyed talking with Ramin. They're a great partner of AMD's. We've been working closely with them, and we're an investor in the Liquid AI startup. The main takeaways from our discussion are that new thinking, taking a fresh start. You heard Ramin talk about a hardware in the middle, an optimization, all the way from the compute engines, from the silicon, through the models and all the way to the application stack, can provide tremendous efficiencies, taking the type of capabilities and agentic processes that today can only be run in the cloud right into PCs and other very, very efficient devices. The other key takeaway is the societal impact, because as we drive down the power needed to run with much more efficient models and provide this in devices which are much less expensive, it's basically a democratization, making AI available to the masses. Thank you for joining us today. I look forward to bringing you more in-depth conversations on cutting-edge technology industry insights and visionary perspectives from some of the brightest minds in the field. You can watch the video show on AMD's YouTube channel or you can listen to audio-only platforms including Spotify, Amazon Music, and YouTube Music. Technology is always advancing, now faster than ever, and I can't wait to share more insights with you next time.